Hi everyone, welcome back to the course on measurement and instrumentation. Today we are going to talk about a new module which is on signal conditioning, and this is the ninth week of this course, and today is the first lecture of this particular module as well as particular week. Okay. Till now in this course we have discussed about the fundamental of measurement systems. We have also discussed about analog meters and the transducers in our subsequent modules, and today we are going to discuss new module which is on signal conditioning, which is a very important perspective of any measurement system. Okay. So, signal conditioning equipments is often required to perform both kind of operation, which is linear and non-linear. Sometimes some of the linear operations that has to be executed by the signal conditioning systems are the amplification, attenuation, integration, differentiation, as well as some addition and subtraction of signals that are generated by the previous steps by transducers or say another system. Okay. In addition, signal conditioning equipment may be required to carry out several nonlinear processes like modulation, demodulation, sampling, filtering, clipping, or as well as clamping, squaring, linearizing, and so on. Okay. These are just some of the examples. You may require to do a number of processes. Okay. To execute all these operations or to execute all these tasks, there are different components of a signal conditioning circuit or signal conditioning system. Okay. You have different excitation systems of a signal conditioning system. Okay. Then you may require different amplifiers, including instrumental amplifiers. Okay. You may require different filters. Then shielding and grounding is very important in a signal conditioning circuit or signal conditioning system. Okay. You have a signal conversion stage where you may require voltage to current converter, current to voltage converter, or say charge to voltage converters, and so on. Okay. And you have also different ADCs and DACs, okay, analog to digital converters as well as digital to analog converters. All are the essential component of any measurement system, and these all are called the signal conditioning systems or part of signal conditioning system. We will try to learn some of them and we will see that how they behave when they are attached in a measurement system or as a part of a measurement system. Okay. So, we have seen that excitation system is one of the crucial component of a signal conditioning system. Okay. The excitation system provides the required electrical energy, maybe in terms of voltage or in terms of current, to a transducer so that it can produce a measurable output signal. All transducers may not have sufficient energy or may not be capable of generate sufficient energy for their operations. Okay. Particularly the passive transducers. So, we know that the passive transducers do not generate energy by themselves and they will require external power for their operation. Okay. We have seen a number of passive transducers in our transducer module, which was the previous module. We have seen strain gauges, RTDs, thermistors, capacitive transducers, all will require a kind of excitation energy for their operation. All right. So, there are typically two kind of excitation, but then this is not limited to only these two, which are DC excitations and AC excitations. You have other kind of excitations like pulse excitations and so on, but we will confine our discussion till DC excitations and AC excitations. Okay. So, this is a typical DC signal conditioning system which uses a DC excitation source. You can see that the first or at the front you have transducer which interact with the measurand. Okay. Then you have bridges which is excited by DC excitation sources or which needs a DC excitation source for their operation. Then you have calibration and zeroing networks. Then again you have DC network which will require another power supply, and then you have low pass filters, and then you have output in form of a DC signal. Okay. As I have mentioned, these DC signal conditioning systems are very much useful in strain gauges, RTDs, potentiometers, and so on. Okay. If you see, these DC excitation systems are very simple. The implementation is also very simple, and they are stable and easy to design while they are used with several bridges like Wheatstone bridge. Okay, so if I have to summarize their advantages, I can say that the DC excitation systems are very simple in circuitry. Okay, they are very easy to implement, so they require only a few components, including some resistors, some excitation sources, and so on. Okay, so easy to design and implementation in laboratory setup is possible. Okay, they are very less complex compared to their AC counterparts. Okay, so you are not using any kind of demodulators in this case, so it makes your system very less complex. Okay, the cost associated is also very low, of course, because you are not investing significant cost in buying a good demodulator. Okay, they are also very easy to calibrate, so output is directly proportional to the excitation voltage. You have a linear relationship between the transfer functions. Okay, so calibration can be done using standard reference inputs. Okay, no phase adjustment like in AC system we'll see is required, so very easy for calibrations. Okay, however, they also suffer from thermal drift. They have very high DC offset errors, and 1/f noise is something these DC excitation systems are susceptible to. Okay, so what happened basically is the low frequency noise actually appears as a data information. Okay, so it's very difficult to segregate between the data and the noise, particularly at the low frequencies. Okay. Several solutions has been proposed, like low drift DC amplifiers are employed in these cases. Sometime you also have a number of AC systems proposed as an alternative to this DC excitation systems. Particularly the carrier type AC signal conditioning systems is one of such signal conditioning circuit. Okay, so if you talk about a carrier type AC signal conditioning circuit, okay, they uses basically a high frequency AC signal which basically acts as a carrier to excite a transducer. Now the output of the transducer modulates this carrier signal according to the measured physical quantity. Okay, so if you see the typical flow diagram of this AC signal conditioning system, it looks like something like this. You have transducers, you have bridges, which is again connected through a carrier oscillator, which is giving a reference to this phase sensitive demodulator. You have AC amplifier in between, and at the output you have, similar to the previous one, you have a low pass filter, and the output is DC. Okay, so although it's a AC signal conditioning system, the output you want is, in, for example, output from a strain gauge, you want in terms of say some DC values. Okay, so if you see, you have a carrier oscillator, or sometime also called carrier generator. So it produces a stable sinusoidal signal, typically in the range of say 1 kilohertz to 100 kilohertz, and then you have a bridge, or sometime called bridge modulator. Okay, so this measured parameter changes impedance and modulates the carrier amplitude. Okay, you have the demodulator, which is a phase sensitive detector which extracts the low frequency measurement signal, and at the output you have low pass filter which removes any carrier frequency and gives DC output which is proportional to the measurement that is done, or proportional to the measurand. Okay, so the signal conditioning in this case is also very simple, but of course a little complicated as compared to the previous one, which was the DC excitation system. Okay, however, if you see, you have the output, but output is very small. It is not very high amplitude. Okay, so you need some post processing of this. Let's understand this with one example. So a typical strain gauge, say having excitation voltage of say 5 volt, and says it's made up of metal and its gauge factor is around 2, which is of course a high for metallic strain gauges, and say strain is about say 1000 microstrain. So the bridge output will be in millivolt only, and the output will be typically in the range of say 5 millivolt or so. Okay, so the thing is, now can you measure this 5 millivolt with a voltmeter, or it can be even lower than this. Okay, we are taking very generous parameters. Say if this output is say 5 microvolt. Okay, sometime it is very difficult to measure these values. Okay, so then second question is, can we send this 5 millivolt or say 5 microvolt to the ADC directly? Okay, what about the noise that persists at this particular low level of voltages? Okay, so now this creates the need of amplification. So without amplification of the output from the strain gauge, or say in general a transducer, you cannot send it to the subsequent stages, and that's why you need amplification stage. And when it comes to amplification, op amp is one of the important component that we would like to learn about. Op amp is nothing but an operational amplifier. So if I talk about op amp is a fundamentally composed, op amp is fundamentally composed of multiple amplification stages that collectively function as one high gain unit. Okay, so this op amp is made up of several components. Let's not talk about that. That is beyond the scope of this course. But what we will do is we will take it as one component, and we'll understand that it has very high gain, particularly the differential gain is very high. Okay, so the op amp have a differential input and a single ended output. So if I have, say, a op amp which is represented something like this, okay, we'll learn about their input. Okay, say V1 and V2 are the inputs at these two terminal, and this is the output. Say if K is a constant, the output voltage is equal to V2 minus V1, and if you see, V0 is directly proportional to the difference between these two input voltages, right? So it has basically these two input terminals, and this is output terminal which is proportional to the difference between V2 and V1. We'll learn about this K and other things in this course about op amp. Okay, so in other words, one input produces inverted output signal while the other input produces a non-inverted output signal. So means that, say, if I have, say, this kind of configuration, okay, so a signal here is in phase with V0 while signal here is out of phase with V1. Okay, so it's about, say, 180 degree phase difference between the signals at V1 and V0. Okay, so op amp has high gain. Ideal op amp basically will have very high gain. Okay, they can act as a differential amplifier. Okay, they have very high input impedance. We'll see how high. Okay, and the output impedance will be very low. Ideally, if it is an ideal op amp, the output impedance should be ideally 0. Similarly, the input impedance should be ideally infinite. Okay, gain is also if particularly the open loop gain is infinite, because input impedance is infinite. All right, so the op amp has 5 functional terminals. Okay, although this will learn as a 3 terminal device. Till now we have seen that there is a 2 inputs and output is giving a certain value in terms of V1 and V2. However, you also have 2 more components or 2 more terminals which are power supply terminals, positive and V negative. Okay, so these are, say, again I will reiterate that this is V in one, this terminal which is marked as positive is non-inverted input. Here this is inverting input, then you have output, and then you have power supplies V positive and V negative. Sometimes we call it VCC. Okay. Now one input is designated by a negative sign which we called inverting, while the other input terminal is designated by a positive sign, okay, which we call a non-inverting end. Okay. So output this V0, okay, and you have a positive and negative power supply. So 5 altogether pins. Okay. These power supply connections are sometimes referred to as supply rails, and the ground terminal here, if you can see, provides a common electrical reference for all part of the circuit. Okay. So again, if I recall the properties of an ideal operational amplifier, you can say that it has an infinite input impedance, or Zi is infinite. It should have a 0 output impedance. Z0 should be ideally 0. It should have an infinite open loop gain, or AV should be infinite. Okay. it should have a flat frequency response over a wide range of frequency, means that its bandwidth should be infinite, okay, and it should have a infinite CMRR, which is the common mode rejection ratio. We'll learn about CMRR sometime after we finish this basic discussion on op-amp, okay. So usually they appear or they are available in form of IC, okay, and mostly it is IC mostly called 741 op-amp, okay, and it is available from several companies. Mostly you will find it in form of a DIL package, which is dual inline package, okay. So it is basically a IC package with two parallel rows of pins that allow easy insertion into PCB or breadboard. You can see a pin connection looks like something like this. I will call it a 741 IC, okay, and the pin connections look something like this. You have offset null at 0.1 and 0.5, okay. Then you have inverting input at pin 2 and non-inverting at pin 3, and then minus VCC is pin 4, while plus VCC is pin 7, while pin 8 has no connection and the output is taken from pin 6, okay. So this is basic IC configuration of a op-amp or 741 op-amp, okay. The 741 op-amp is a general purpose operational amplifier widely used for amplification, for filtering and for signal processing applications, okay, and its standardized design and broad operating conditions make it suitable for most basic analog circuits, and you will find all the circuit which utilizes op-amp containing this 741 IC chip, okay. So then we have now basic understanding of op-amp and its ideal characteristic, but ideal op-amp does not exist, okay. So you have more practical op-amps, okay, and model of real operational amplifier looks something like this, okay. So the input network is specified as a resistance from each input to ground as well as an input to input isolation resistance, something like this, okay. The equivalent resistance is Rin, or we can also call it Zin, okay. In most operational amplifier, these resistances are typically on the order of several hundred kilo ohm or higher, because we have also learned that this Rin is very high. The output source is a dependent source. Basically, if you see, the V out is basically a dependent source. So it is basically a voltage controlled voltage source, VCVS, okay, and the value of the source is given as in E output as AV, say open loop gain of this op-amp into the difference between these two inputs, or V in plus minus V in minus, okay. Because the input stage operates differentially, the voltage difference between the two terminals is multiplied by the system gain, which is AV, okay. Now this signal is presented to the output terminal through the final stage output impedance, which is this Z out, okay, and in most of the cases the output impedance of the operational amplifier is very less, typically less than 100 ohm, okay, and we have seen that for ideal op-amp it was 0, okay. So for the level of load resistance, which are practically in terms of certain kilo ohm, generally used across the output terminal of the op-amp, Z out is in the range of say 100 ohm, which can be considered as negligible, because when RL is, say, if you are connecting some load, RL is certain, say 100 kilo ohm for example, okay. The Z out, which is say 0.1 kilo ohm, say 100 ohm, okay, it is kind of negligible in as compared to the practical RL values or the load values, okay. So based on whatever we have learned till now, we can say that there are three important characteristics of a op-amp. So three notable features that characterize this op-amp model are: the input impedance Rin here should be infinite, okay. We have seen that it is few hundreds of kilo ohm, but ideally it is infinite, okay. The actual value may be of the order of several mega ohms or hundreds of kilo ohms, okay. The output impedance Z out in this case should be 0, okay. So the op-amp is constructed so that its output voltage depends on the difference between the two input stages. So V out is actually AV into V in minus V in plus minus V in minus, and say this difference here you can see I am calling this difference as VD, okay. So if I am calling this VD, V out is equal to AV into VD, Alright. So the open loop, the third characteristic of this operational amplifier model is that the open loop gain is infinity. Okay. So VD, we have seen that it is V in plus minus V in minus. So this terminal, the voltage at this terminal V in plus minus V in minus. Okay. This denotes the net differential voltage across the op-amp terminals VD. Okay. So open loop voltage gain AV, which is the ratio of V out to VD, should be infinite. Okay. Although practically it is not infinite, but it is very high, of the order of few lakhs. Okay. So AV is equal to V out divided by the differential voltage at the input terminal. VD is equal to V in plus minus V in minus. Okay. And AV is the open loop gain, which is about 1 lakh or even more than that. Okay. This means that the net differential voltage is increased at the output terminal by this particular factor, because we have seen that V out is equal to AV into VD. Okay. So if overloads are to be avoided, it is necessary to restrict this VD value to those values that will keep V out at least below the magnitude of the supply voltage. Okay. So accordingly, for the case when, say, if you have AV equal to 1 lakh and this VCC as plus minus 15 volt, VD must be limited to VD is equal to this V out by AV, which is, say, V out is reaching to, say, 15 volt. So 15 divided by this AV, which is 1 lakh, which is equal to 150 microvolt, just for example. Okay. To give you an idea of the numbers. Okay. So the operational amplifier exhibit very high gain, causing the output voltage to increase sharply with small change in the differential input voltage. So VCC we have seen, say, in this case 15 volt, we have seen that VD is equal to 150 microvolt and AV is, say, 1 lakh. Okay. So once the differential input reaches a small value, say 150 microvolt, I am calling it now a threshold value, the output quickly enters the saturation. So the value of this VD at which the output reaches the saturation is known as threshold value in case of our op-amp. You can see this from this transfer characteristic. This is a plot between V out versus VD. Please note that this VD is not a single voltage, it is the V in plus minus V in minus that we have just seen. Okay. So there is no point of plotting V out versus V in plus or V out versus V in minus. You plot basically V out versus the V in plus minus V in minus, which is the VD value. Okay. So this is the value of the threshold voltage at which it enters into the saturation. Okay. So once the differential input reaches a small threshold value, say in this case, for example, 150 microvolt, the output enters into saturation. Okay. Here VTH represents the threshold value of VD beyond which saturation sets in. Okay. The threshold value in this case is of course much smaller than VCC, and the slope of the curve represents the open loop gain AV. Okay. The transfer characteristic indicates that the amplifier region of the op-amp is this one. Okay, this particular region, and in this region V out is AV into VD, which is restricted to an output voltage range of certain value, okay, between certain maxima and minima. Okay. When the differential input voltage exceeds the threshold value, internal stage enters into saturation. As a result, the output voltage remains fixed at its positive or negative saturation level outside the linear amplification region, and I am talking about this particular regions. Alright. So positive saturation happens when the output reaches its maximum limit, which is, say, VD is greater than or equal to VTH. Okay. So VD is crossing this VTH value, or at least it is reaching VTH, and accordingly your V out is actually saturating to the maximum value. Okay. So V out in this case is reaching the saturation value. Alright. Similarly, negative saturation happens when the output reaches its minimum limit, and negative saturation is setting in at this particular value, and VD is smaller than or equal to minus VTH, and at this particular point V out is equal to minus V saturation. Okay. So I hope that the basic understanding of op-amp is very clear to you, what we will do is we will keep our discussion on op-amp continues in our next lecture as well. We'll also learn different circuits that can be derived based on this op-amp. In fact, our major discussion will be on instrumentation amplifier, and the op-amps are actually the major building block of those instrumentation amplifiers as well. Okay, so with this we are finishing this particular lecture today, but we'll keep our discussion on op-amp continue in our next class also. Thank you.